Wait, can everyone see
Yeah,
my
we
screen?
can.
Okay, good. Okay, so let's do the try data structure first. Let's start with this. So try, right? So they asked me to design a type ahead, system. So what a type ahead system basically is, so you see Netflix actually has a search bar, right? And when I go there to search for a movie, let's say one of my favorite movies, Scorpion, right? Scorpion, or let's actually use a two-word movie. Let's say Detective Chinatown, right? Detective Chinatown. So what they want you to design is, as somebody types detective like this, D-E-T, there's going to be, a couple of suggestions here. That'll be like maybe detective, maybe Ghana Town, right? Maybe what movie begins with D-E? Like anything, right? Maybe deepening, right? Like something like that. So a couple of suggestions, and as you type, the whole thing gets filtered, right? Then maybe as you type detective, deepening will be ruled out, and everything will be ruled out, right? And then and so on and so forth. So this is simply a type ahead system. That's the system they wanted you to define. So usually when you come across questions where it's in the format of words changing, a collection of words and kind of like filtering through them, the data structure we typically use is the try. Now, this is not the only application. The other application is, those of us who used MS Word, decades ago when we were born, there's this thing called Thesaurus or something, right? Where, you type words and then it predicts for you. Same thing for dictionaries. All these, implementations actually use the try data structure. And it's very clear why they use the try data structure very soon. So let's basically look at a structure. The try data structure actually has the roots, right? That's the roots node. And then it has a couple of children, right? So here we're going to consider the context of, of words, right? Or something like a dictionary. So let's assume you have a couple of words, A, B, C, a couple of words, let's say A, B, C, D, A, B, C, D, E. You have A, E, C, right? And you have A, let's say A, M, N, right? And I want to insert these words into a try, right? So we are going to look at the insertion operation for the try data structure. So to insert, what you do is you first go to the root node. You first go to the root node here. And then, so let's say you want to insert the first word, AMN. You go to the root node here, and then you ask, does the root have any child which begins with A? That's the first thing you do. Does the root have any child beginning with A? Right? Currently, it has no child beginning with A. So what we do is that we insert A here, right? So we've inserted the first A. The next thing we do is we now go down, that's A, right? That A is now a node. We go down that node, and we're like, does A have any child M, right? Currently, this A has no child M. So we create a child for A and put M there. Then we do a similar thing again, right? So you can see some kind of recursive pattern there. You can also use a loop. We look at the implementation. So we're like M. Does M have any child N? Currently, M has no child N, so we put N there, right? We put N there. An optimization we do is that when you've got to the end of the word, what you do is that you kind of mark it, right? So you can mark this by saying it's end, right? So let's just circle it with red, right? And basically that's how it works. So now let's say we want to insert the next word. The next we want to insert is AEC, right? So to insert into the try, first thing you go to the root node, then you ask, does the root have the next character as a child, right? So the next character is A, right? That's the first character, you're inserting AEC. So you're like, does the root have the first character as a child A? And A is indeed here, right? So we're going to go down that A route, right? We don't create a new node because A already exists, right? So we come down, this route, even like A, do you have E as a child, right? A has only M as a child, it does no E as a child. So we create a new node here for E, right? Then we move on. We're like, okay, does E, so we are here, does E have a child C? E has no child C, so we can create a node for C here, right? So you can see basically how word searching is going to work, right? So if I want to see if a word, if I want to see, let's say, let's add one more word, then we look at a couple of, examples. Now, let's say we want to insert the word, let's say ABC, right? So again, we're going to use A is already here. B is not here, so we have to create a new node for B. We're like, okay, B is here. And then C is here, right? Now let's do A, B, C, D. So we come to the root first, A, right? A, there's B here, there's C here, and then we can do D, right? We can do D. So now let's say they've given you a question and they want to check if a certain word is in a dictionary. So assume you have a dictionary, right? You want to put these words into a dictionary, you can simply put them into a try data structure like this, right? And if I want to check if a certain word is in my dictionary, the searching becomes relatively simple, right? So let's take a word, for instance. Let's say you want to search if the word, let's say ABD, it's not try, right? It's not dictionary. What we can do is that we are like, okay, first come to the root node like this. So we are the root node, then we're like, is A a child, right? Then we're like, yes, A is a child. Then we go down the child A, right? Then we have the child A. Like, okay, after A is B. Is B a child to A? We're like, yes, B is a child to A. We come to B. Then we're like, okay, the next character is D. Is D a child to B? It is not. So we can return false, right? We can simply return false because D is not a child here. The same way, if we want to see if a word, let's say AEC is in a dictionary, it's a word in our dictionary, we can do the same thing. We come A, then we come A, and then we come C, and it's in, right? So that's basically how the trie-data structure works. It's also called a prefix tree. A prefix tree. Now let's see why it's called a prefix tree. Assume you have a question, I don't want you to, you have a list of words like we have here. Let's clean this up. And they want you to return all words that begin with, let's say, AB, right? They want you to return all words that begin with AB, right? All you have to do is you can simply, traverse, come to A, and then come to B, right? Once you come to A and you come to B, you know that everything, right? Everything that's from B going, right? Including B itself is actually a word, right? So for instance, assume I had, another one here, another one here, another one here, another one here. Once I come from A, A to B, every word here I know it's actually, a word whose prefix is AB. Prefix simply means a word that begins with, those characters, right? So ABC, ABD, and so on and so forth. So it's called a prefix tree. That's the other name for the trie-data structure. The last thing you want to notice, the last thing you want to keep in mind is sometimes we care about if the thing the branch you have traversed is indeed a word, right? It's indeed a word. So for instance, let's say they want to ask if the word AM is in this dictionary, right? AM is in this dictionary, right? Here, AM is not a word in this dictionary we have here. It's only a prefix, right? Because there was no word AM that we inserted, right? There was no word AM. So if you come from A and you come to M, realize that M does not end a branch, right? M does not end a branch. Can we all see it? So it's actually a prefix. That's why we did this red circling. So when you finish inserting a word, usually what you do is that you kind of mark it in a way, right? You mark it like this, red. That means that the word ended here, right? Here you marked it with this, a word ended here. We inserted ABC, ABC. There was a word that ended here, right? And there's a word that ended here. That is basically how the trie-data structure works. Its main operations are insert, find, insert, and find. That is the main operation. Deletion is kind of simple, but it's a bit tricky. But these are the main operations of the trie. Does this make sense? Or is it a lot? Does this make sense? Does this make sense?
Yeah, it makes sense.
Yeah. So the couple of questions, we probably look at one when we are done, but that's basically how it works. Its implementation is relatively simple. So this is how we can implement the trie-data structure. So we're going to use an object-oriented approach, right? So for every node here, we're going to represent each node with a class, right? Each node is going to be represented with a class. So let's write the implementation for the class. So we can say class trie node, right? So trie node. Then let's write the def init. So we can be like def init, right? And now, so let's put self here. Each node is going to have two things, right? So you see each node, this is a node, right? This is a node itself, right? This guy is a node here and it has children, right? Each node has children. So we can be like self.children, right? Self.children. And I'm going to use default dict. And I've explained default dict before, but I'll touch on it again. I'm going to be like default dict trie node. That simply means that, so what this simply means is that each node, right? If you see here, each node, its children is going to be a dictionary, right? It's going to be a dictionary where the key, or you're going to do something like this. Please follow me carefully. It's a bit recursive, but it makes sense, right? So each node has children, and its children is a dictionary where the value is also a trie node again, right? This is basically what it means, right? And that is basically what we're going to do here. If you have, let's say, the word A, give me a second. Okay. So if you have the word A, right? So let's look at this. So let's consider the word A here, right? A here. A is actually a node here, right? And has children. And each of its children is also a node, right? It's also a node on its own, right? That's what we have here. So if we were considering the word A, so look something like this. Let's look at it here. We have node A, right? That is this node we have here. Its children is also a dictionary, right? Where the key, there's one key for the letter M, right? And that is also a node, right? So that is also a node M. Then it also has a child E, right? That is also node E, that is also going to be a node E, then has a child B, that is also going to be a node B. This is a pattern you actually come across often when you're designing like recursive data structures, where the name of the data structure also appears in its initialization, right? Does this make sense? Does this make sense? That a node has children, and the children is simply a dictionary, right? Where the key is going to be like the letter itself. So like M. So that is how we're able to be like, that's how we're able to check, hey, is A a child of the roots? Is M a child of this one, or of what you call of the node? We can simply be like, if M in, right, node A dot children, right? We can simply use this to basically check, right? Yeah, and the last thing it contains, as we said, is self.isEnd, right? Is end. So what that basically does for us, we can initialize it to false. Is this current node an end to any word, right? So here, if I come to A and I come to M and I come to N, I'm like, hey, if the word has ended, then I can simply set is end on node N to true, right? To true. And that's basically, the definition for the try node itself. Then the try itself, right? Let's write the implementation for the try itself. Can def init again. Then all we need to do is initialize the roots. Self.root is simply a try node. You can simply create a try node here, and then we are done, right? So this self.root you've just written here, this definition is simply this guy here, right? This parent guy here, right? That's something people usually forget, but that's simply the thing you have here, right? So if I want to, let's say, do an insertion operation, the code is kind of like too simple to believe, in my opinion. So to insert, so let's say I want to insert, let's say self, and I want to insert, let's say, a word into it, right? So let's say word, right? So we said the first thing you do when you want to insert is first get the root node, right? I call it current. So current is going to be self.root like this, right? So now assume we are standing at the top of the try, standing here at the top. We have nothing inserted, right? And then we can be like, for every character in word, right? For every character in word. So let's assume the word we're trying to insert is A, B, C, D, right? So for every character in word, I'll first check if, right? If the character in current.children, right? So current is actually a try node, right? I can actually annotate it if you want. So in current is actually a try node, right? And it starts at self.root, right? That is this guy here, right? Then we check if C, right, in current.children, if it is there, right, all I have to do is I simply move current to current.children.get C, right? So basically what I did right now is I check, so let's assume A is already here, right? And let's assume B is here, let's assume C is here, right? Then I check, is the first character in word, right? That is A. I check, is A in the children of current? This is current. Current starts at the root, right? Starts at the root node, right? Then I check if C, right? That is the character. If A is in the root children, then just move and come down here, right? Just move and come down here, right? And continue your search from here, right? And continue your search from here. Does that make sense? That's all we are doing like here. If C is already a child in A, just move down and continue the search here, right? Because then that's when I'm going to go to the next character, because the character C is going to be A, then it's go to B, then C, then D, right? So that means that now come here and search and look for, and look for B, right? If not, right, else, we can simply create the node there, right? We can simply create a node there. Does that make sense? Does this first part make sense? If C is in current children, we just move down, right? We just move. So assume current is a pointer, it starts from here. But if A is already in, move it and come start from here. Does that make sense? Does that make sense? I know it's a bit something, but kind of makes sense. So else if it is not in, right, we can simply just create it in, right? So we can simply be like current.children, then we can create an entry for C. Because we use default date, this code can be very simplified, but now we just explain. So let's just go ahead with this. So current.children.c is we can actually just create a try node here, because we're now putting it in, right? We assume it is not in, it's a try node here. Then we simply move current forward, right? We simply move current forward. So current is going to be current.children of C, right? And we are done, right? So that's basically what we do. So we are like, hey, so let's just do that visualization also. So we are like, we are still putting the word A, B, C, D in, right? A, B, C, D in. So you're like A, you're like, is A here? No, A is not here. Then, right? So we are doing the else block, right? Then create a slot for A and put A here, right? Then move current to come standard A, right? So that's what we just did here. Move current to come standard. Then we come again. Now the next word, the next character is B, right? As you can see, B is the next character. Then like, is B in the current children? B is not there. Okay, then create a try node for B and put B in. Then we come again. Is C in it? They're like, no. Then do C, right? Is D in it? You come again because you're moving, current. Then it comes here, right? Then after the for loop has ended, you want to tell us that, right? You want to show that B is indeed the end of a certain word, right? That a certain word ends at D. So after the for loop has ended, you simply do current dot is end to be true, right? Because that's simply what we did here, right? Current dot is end is true. And that's basically the try data structure, how you do insertion. And AC is actually not that hard, right? And if somebody looks carefully, this line of code is simply the same line of code, right? So we can actually cancel this guy and just use an if for this, right? Because we use default dict, you can even change everything into 2 lines, right? If you use default dict, you can simply do this. Like this, all this thing can simply turn to current is equal to current the children C, and that is the whole thing. And that is basically the whole thing. If you want to do insertion is, find. Find is actually the same thing. Find, you start here, current is equal to this, then you simply do the same for loop. You just change 1 line of code here, then you can simply return current.isEnd, and that is it. That will be in the questions we try. I want us to go to graphs. But for that, does anyone have a question? I just want to have an idea of how the try data structure works. It's usually used for things like this. You put words in, like have a dictionary of words, then you put things in. You want to say, hey, is there any word that begins with this prefix? Is there any word that is this? Is there this word in my dictionary? When I had my interview last cycle with Netflix, I hadn't done system design before, but I had learned the try data structure from like 2021 when I first started this whole thing. So they were like, how are we going to store these words, right? Like the words that will be, suggested to the user, right? And I knew the try data structure is the one that is used for things like dictionary, thesaurus, and all of those things. I was like, oh, use the try data structure and everything. Yeah, I was like, yeah, that's it. So even if you don't learn system design on something, just know the data structures well enough and you can apply them when you have to. Good. Can we go to graphs now? We'll give a couple of questions. There are not many questions on tries, but we'll give a couple. And with this understanding, I think you can definitely, maneuver your way through or even understand the solution when you learn them. Can we go to graphs now? Anyone? If yes, yeah, in the chat or an emoji. If no, be like, wait.
Yes, please.
Okay, good. Okay. Now let's take a look at graphs. Graphs are kind of like, some people say graphs are hard, but in my experience, I feel like graphs are some of the data structures you can easily, find your way through, because many of the graph questions you come across, right? When we did dynamic programming, we said that some questions are very similar. They belong to like, a class, a family, right? And I think some graph questions too are like that, right? Like in 2021, I had done, let's say, 2 main graph questions, right? One was cost schedule, right? The question we'll be giving out to on today. And, I learned graphs very late because people used to make a lot of noise about it because there are many algorithms associated with graphs, like, Bellman-Ford, minimum spanning tree, and all those things, right? So I learned that question, cost schedule, I learned it well. Then I had a couple of, interviews like DoorDash and all these places. And it was as if cost schedule algorithm was working for everything, right? Like, because that's how graphs work. It's like, just use a for loop, exploit its neighbors, check if there's a cycle, return true or return whatever you want. And it just works, right? So I just say be open-minded for graphs, learn a few questions like really well, learn the algorithms like so well, get algorithms ingrained in your mind and just apply them and tweak them however you can. Okay, so let's see how a graph is. So we've already done trees, right? And we said, let's focus on a binary tree for now. And we said a binary tree simply looks something like this. A binary tree is simply a tree with at most 2 children, right? And if you remember, we actually mentioned that a tree is a graph, right? A tree is a graph. So a tree is a graph, right? But then it's a special type of graph. It is a graph, right, that is fully connected, right? So a tree is fully connected. That means that there's no node that is like separates or, somewhere on its own. A tree is a graph that is fully connected and has no cycles, right? It is acyclic, right? Has no cycles. That means that if you're traversing, right, and you just come, and you come down here, like you can see every node just once. Like if I come here and I come here, right, I can't, like move from here and then, or like I can't, let me make it simpler. Like there's only one path to every node, only one path to a node. that's another way to think of nodes is acyclic, right? There's only one path to a node. That means that there's only one way to get to this node here, only one way. You can only, like, from the roots, you can only come from here and then come from here, right? The same thing for this node. There's only one path, from the root to come to that guy. That's what I mean by acyclic. That is what a tree is. It's an acyclic graph, right? But then the general graph that we're coming to do does not have to be fully connected and does not have to be acyclic, right? So this is a graph. This is a graph, like this whole system, like this is a graph, though it is, disconnected. This is also a graph. Actually, linked list actually graphs. This is also a graph. This is a graph, right? This is also, because there are many ways to get to this guy, right? Like you can like go here, go here, go here, go here. You can also see itself, right? And so on and so forth. The other thing I wanted to talk about is the direction of a graph. So let's take a standard graph like this. Let's just make it acyclic. These are what we call the vertices, right? The vertices, or what we call the nodes. Some call the nodes, I guess I even do. And this is what we call the edges, right? These guys are the edges, right? So the vertices and the edges, very important to know. Now, the edges may either be directed, right? They may be directed, they may have arrows pointing this way, right? Or they may be undirected, like the normal one we had, where, there's nothing, showing this, right? So this is an undirected graph. And this is a directed graph, right? So a directed graph simply has arrows that shows the relationship. So if we take something like this can be, maybe a course and maybe a student, right? Or maybe a car or something, a car, and then, a person. Then we're like, okay, so this edge simply shows the relationship, right? This edge shows the relationship between the car and the person. So this can be car belongs to this person, right? That's basically how the graph structure is. So it basically shows relationship. So this is a car, then this car belongs to a person, right? So that's one way of the, the directed graph. Then let's say the undirected graph like this. So like Facebook friends, right? So this is human being A, human being B, right? It's the same as, so let's say the edge is a friend of, right? It's a friend of. So you can be like A is a friend of B, right? And if A is a friend of B, B is also a friend of A, right? So there's no need to, do this thing like this. You can simply use, an undirected edge to simply mean that this means it's a friend of, right? So that means that it goes in both ways, right? That's one way that's one application of it, that this is a friend of this is also a friend of this, but we can simply use, an undirected one to also represent it. So directed edges have pointed arrows, undirected ones have no pointed arrows, right? Does that make sense? There are cases where you actually have to consider both. And it's possible for the arrow to point in both directions, right? That A is a friend of B and B is also a friend of A. Or when we don't care about specific, descriptions of the relationship like that, so we can simply use an undirected edge. Does that make sense? Do we have the picture of the graph? This is just a picture of how the graph data structure looks like. Just a bunch of, whoa, someone is so excited. Okay, so we just have a bunch of nodes, right, that are connected by edges. And that's simply what a graph is. Okay, can we move on? Can we move on a bit fast? But that's basically all there is to it, honestly. I guess we on. All right, so let's go to the next thing about graphs.
Yes.
Yeah, let's go to the next thing about graphs. Graph traversals. So if people remember tree traversals, we discussed that there are many ways to traverse trees. And I'm using trees because trees are graphs, right? So we talked about in-order traversal of a tree. We talked about pre-order traversal of a tree. We talked about post-order traversal of a tree, right? And then someone actually hinted to me like last week that we actually didn't write the algorithms this year. I know last year summer, we actually did write it out. And I was like, this is the only thing you need to keep in mind. So in order, so let me just go over it briefly for a tree. So assume we have a tree like this. Let's say 1, 2, 3. In order traversal of a tree, just look at the word here. The word is in, right? In, right? So let's say the function to traverse is, let's say fn. So let's say you have a function called def fn, right? And you have the roots of the tree, or let's say you have some node. I like to use node, right? In order traversal, the algorithm is simple, right? So it simply process, call the function on the left subtree. Then you process the node, process the current node. This is just all you need to know. Then call the function on the right subtree, right? Now, if you want to do pre-order, I'll show you an easier way to put in your mind. Just follow me. A pre-order traversal, right, is typically the same thing, but the only thing is pre means first, right? So just take this guy, pre-order traversal, just take this guy here, right, and move that guy here. and you're done with pre-order, and that's pre-order traversal. In means inside, right? So just move it here. Pre means first, just move it here. And that's how pre-order traversal works. Post-order traversal, post means after. Just take this guy and bring this guy here, and then you are done, right? So that's how you write the traversal implementation. The base case is just the base case. Like if not node, you just do whatever you want. If not node, right? That means that if the node is like an empty, like this guy has no, left and right child. So that's like if not node, right? So if you look at this traversal, so let's just do pre-order traversal. Let's move this guy. Let's move. So this pre-order traversal, right? But then you can see that we only have to call the function, right? If not node, okay, blah, 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 function, right? We see that we only made 2 recursive calls, right? Why? Because we know that a binary tree is going to have at most 2 children, right? At most 2 children. So we only have to, make 2 recursive calls on the left child and on the right child, right? But graphs are different. Graphs can have, as many, relationships as possible, right? The tree is going to have only 2 relationships at most, the binary tree, right? Only 2 relationships at most, but the graph can have more, right? Can have more. So now let's look at, even if we come to graph traversals, let's look at how we can show this relationship, right? So code-wise, you can't, write this as a code, right? This thing can be passed as an input to some function. That's not possible, right? So there are 2 main ways of representing graphs. That almost escaped me. So graph representations. So the first common way is the adjacency list. Adjacency list. The last one is the adjacency matrix, right? So this is how the list one works. So for every node, so let's draw a simple graph here. So graph 1, 2, 3, 4. Let's say it's directed. Let's use a directed graph, right? So if I have this graph, I hope it's clear. So for an adjacency list, we can just create, a node. So node 1, right? Node 1. Then it's what do you call it? It's neighbor. So 2 is a neighbor and 4 is a neighbor. Can just be put in a linked list, right? So 2, let's just do it this way. 2, then a linked list 4, right? So this is one way. Then we take the node 2, right? Node 2, does it have any neighbors? Yes. We prefer to call them neighbors in graphs instead of children, right? Then 2 has a neighbor 3. So we put that here. Then we come to node 3. Node 3 has a neighbor that is 4, right? And node 4 has no neighbor, so we can just leave it empty, right? And that's the adjacency list. Very simple implementation. You can simply use, so somebody can actually just use a hash map, right? You can simply use a hash map where the key, right, is the node value itself. And so this is the key, right, is the node itself, and the values are simply a linked list, for what do you call it, for its neighbors. So that's just one way. The adjacency matrix is a bit different. And one way to use the adjacency matrix is, let's say we have 1, 2, 3, 4 here, the same nodes, 1, 2, 3, 4, right? What we do is we can do something like this. I don't know, people use this guy. I don't know why they use this guy. It's sometimes fast though. Let's see. Okay. So for that, if there's an edge from 1 to 1, right, we just write a 1 here or 0, anything you want, right? So let's see something. So there's an edge from 1 to 2, from 1 to 2, right? From 1 to 2. So from 1 to 2, there's an edge. We write 1 here, right? There's an edge from 1 to 4. From 1 to 4, so we write 1 here, right? Then we can fill all the others with zeros, right? All the others with zeros, right? It's implementation dependent, but that's basically how it works. So there's an edge from 2 to 3. So from 2 to 3, there's an edge. So we can put 1 here, right? Then the rest, we just put zeros here. Let's put zeros here. There's an edge from 3 to 4. As you can see, 3 to 4, there's an edge there from 3 to 4. So we can simply 3 to 4, there's an edge, we can put 1 here, right? Then you can put zeros in the others. Then from 4, there's no edge to anywhere. So we can simply do this. And that's simply an adjacency matrix, right? So from here, I can actually just come here and be like, okay, so if I want to find the neighbors of 1, it's simply, so if I want the neighbors of 1, it's simply, those numbers where there's, a 1 in the slot here. So you just have to be good with matrices to just manipulate this. Usually we use this, like I use this, like this is so simple to create, right? This is very simple to create. If you're using Python, this like, even Java or anything, it's actually very simple to create. But I can simply use a hash map or a dictionary to create this, right? So if I use a hash map to create this, I can simply, just make my key, the number itself, right? Or the node number. Then my value, the values are simply the list of, the list of its neighbors. So if I see 2, I'll do, you don't even need to use a linked list, honestly. If you look, if you can just use a normal list, right? You can simply make it 2, right? I'm just showing you how, like, adjacency lists are so common. You know, there was this project I worked on with someone, and the person implemented, you know, their graph using this guy here, right? And I'm like, well, you do this. I use this. Well, his work though. I mean, mine also worked, by the way. So yeah, this is kind of like very simple in my opinion. So this is just, you know, a normal list, right? And that's it. So one thing I want you to keep in mind is you have to learn to create an adjacency list from in a graph question, right? And there's a question we'll be looking at today. Actually, let's do that question right now. Okay, so the question is called cost schedule, and this question saved me a lot in 2021. Cost schedule, right? So let's look at the concept of cost schedule. So this is how the problem statement is like. So there's a couple of, there are courses you can take in a school, right? So let's say courses 1, courses 2, courses 3, courses 4. Please follow me carefully and understand this question. It's very important, trust me. And many graph algorithms actually revolve around this concept. So concept 1, course 1, 2, 3, 4, 5, 6, and 7, right? And then there's something, right? There's kind of like a restriction that you can't take all these courses anyhow you want. Some courses have prerequisites, right? So to take course 2, right? To take course 2, you should have taken course 1, right? To take course 2, you should have taken course 1. To take course 1, you should have taken course 4, right? To take course 1 again, you should have taken course 6, right? Then maybe to take course 5, you should have taken course 2, right? Then maybe course 7 does not need any guide, right? Course 7 doesn't need to be, doesn't have any prerequisite. You can take course 7 anytime you want. Or even let's trick ourselves. Like to take course 7, you probably should have also taken course 6. 6 works? Okay, 6 works, yeah. So these are the courses you can take in the school, right? Let's say KNUST or whatever school you want, right? But then there's a restriction, right? Called the prerequisites. Where to take, course 2, you want to take course 2. So this one is like main, let's say parent course. Let's make it this way to make it simpler. And this, let's say child course, right? Or we can simply say course and prerequisites. So course and prereq, right? And then the question is asking you, is it possible, right, to take all these courses? And that's the question, that's the whole problem. Is it possible to take all these courses? Is it possible, right? And the question you should ask is, when is it not possible, right? When is it not possible? Anyone? When is it not possible to take all the courses, right? When is it not possible to take all these courses? When is it not possible? Any case you can think of. When is it not possible to take all these courses? It's a concept we actually mentioned a few minutes ago in graphs. When is it not possible to take all these courses? You can type it in the chat. You can also say it out. It's just a suggestion. Anyone? When? Yeah, Abednego, let's go. Yeah. John, yeah, you can talk.
Yes. So looking at the question, if the course is, let's say, just maintain this, and imagine before I take course 6, I need to take course 2, which become a cycle.
Good. Exactly. So, and that's the whole thing, right? So they basically check, when a prerequisite is not met, that's true. And when it's a prerequisite is not going to be met, it's what John just said. It says if there's a cycle, right? So for instance, they tell you that to take course 1, right? You have to take course 6, right? That's what you can see here, right? To take course 1, right? You have to take course 6. Then they tell you to take course 6. I think they are like to take course 6, you have to take course 2, right? You have to take course 2, right? As you can see here, to take course 6, where is it? Let's just add that. It's imaginary, right? It's just an imaginary case. So let's say to take course 6, they're like, you have to take course 2, right? To take course 6, that's what we just did here. You have to take course 2. Then you can see that to take course 2, you have to take course 1, right? To take course 2, you have to take course 1, right? That tells you it's not possible, right? That, hey, I want to take course 1. You're like, nope, I have to take course 6 first. I'm like, okay, let me go and take course 6. I go to take course 6. You're like, oops, take course 6. You have to take course 2. I'm like, okay, let me go and take course 2. To take course 2, then they bring you back to where you were, course 1. That is a cycle. That means it's never possible for you to take the courses, right? Does this thing make sense? Like if there's a cycle, right, in the dependency, it's not possible, right? So they're basically asking you to check if there's a cycle, right, in your graph data structure. So you can simply take this this requirements thing and let's construct a graph out of it. And if you see, a cycle in it, you can simply be like, hey, return false because it's not possible. Does this make sense? Does this make sense?
Yeah.
Yes, please.
Okay, good. So let's try to draw, a dependency, out of this. So we can actually, sketch it out and see. So we are like to take course 2, right? Let's take course 1. And then we like to take course 1. Let's take course 4. Then we like to take course 1 again. You have to take course 6. right? I'm just writing these things, like just these things. Then to take cos 5, take cos 2, right? If a node already exists, we let's just connect it to it. Then like to take cos 7, take cos 6, right? We didn't need this guy. So in fact, if we had this, right, we realized there would have been a cycle here, right? Like if we had to take cos 6, take cos 2, there would have been a cycle here, and consider cycle. They go forward, go down, go back, right? This is a cycle, and we don't want that, right? So without this case, realize that it's possible to take all these courses, right? It's possible to take all these courses. Now let's go to the next thing, right? The next thing in solving graph problems is usually when you have the structure like this, you start with the nodes with no incoming edges. What do I mean? So we have something called degree, the degree of a node. Degree of a node, right? And there are two types. We have the in degree and we have the out degree. So in degree is simply the number of incoming edges to it, right? The number of edges that are incoming. So if I take 2, for instance, the in degree is 1, right? Because there's only one node here, like this guy here, that is coming into 2, right? And this out degree, the number of edges leaving it is also 1, right? The out degree is also 1, right? If I take 1, the in degree is 1, but the out degree is 2, right? I hope that makes sense. So when you're doing graph problems, it's usually simple, right? To if you have it your way, to start with those with the lowest in degree, and realize it's actually the same thing in this question, right? That the courses with no prerequisites, right? That means they have no, what do you call it? They have no coming in. Those courses are better completed first, right? Because if you start at any random course, let's say 1, you can't complete 1. You have to go and complete its prerequisites, right? So let's say 4, you are done. Why can we just complete 4? Because 4 has no, nothing else, right? Like 4 is not dependent on any guy, right? 4 does not depend on anything. So I can just complete 4. Then I come back to 1. I'm like, hey, 1, I need to complete 6. 6 is like, sorry, you can't complete me. Go and complete 7. Then you come to 7. 7 has no, no in degree, right? So we can simply compute 7. Then we do, and then so on and so forth we go. But now let's see how, so the question, right? So if you have a question, it's going to give it to you in this format, right? Courses, it's going to give you the input in this format. It's going to be like courses like this. Then it's going to be a list of lists. So let's say 2, 1, 1, 4, right? I'm showing you how the input is going to be. Then 1, 6, then 5, 2, then 7, 6. And it's up to you to kind of visualize it this way. What we just drew is just this visualization, just something in your head, right? So now, if you have the question like this, rule number 1, construct a graph out of it. And now we have shown 2 ways of representing graphs, right? Either to do it the adjacency list way or the matrix list way, right? And I said, just go for this guy. We'll save you. Okay, so now let's just create a graph out of it. So I usually just call it graph like this. And I use default dict. You can simply use a normal dictionary. Each of them works. Default dict. Then, so if you saw, we said that the key, right? The key can simply be, the value itself, like the graph's value. So like 1, then the value is simply a list, right? So the values are going to be a list. So default dict, you pass the type of the values, your list like this. Then I can simply loop through, these are pairs, right? So let's just call the first character A, then the next one B, right? So we are like for A, B in courses, right? I just destructured it. A, B is just going to, take it out a pair, right? Then we can simply do graph, right? Graph of A, right? Dot append B. So that is like, if you take it, so the first loop iteration, right? A and B are going to be like this 2, 1, right? So assume this is your graph. So you're like graph of A. So this is our graph, dictionary. So get A, then, because I did this default text list is to initialize A's values to the empty list if it is not already in, right? If it's not already in. So I'd be like graph of A dot append B, right? Then assuming I see it again, then it will be like, if it's already in, so just append it to this, right? That's a part of default dict. I don't need to do if A in graph, else this, right? This will just handle everything for me. That's a cool thing. And we talked about it too in previous videos too, right? At the end of this for loop, that I've had my graph beautifully created, and it will look something like this. 1, right? So the first entry was 2. So 2 will contain 1. Then 1 will have 4 and 6, like this. Then 5 will have 2. Then 7 will have 6, right? So this is how the graph is going to look like. Let's build something around this. So this is how the graph is going to look like. So we just built our graph, right? And this for loop just built it, right? So you see how it's simple to just take, an input like this and just construct a graph out of it. It's just a for loop in a dictionary. Very simple and very clean, right? Then the next thing I want to do is I want to check if it is possible to complete the courses, right? and then somebody can think of DFS. We can simply do DFS. There are two main ways of traversing graphs. So if you saw the tree one, here we did, it was actually a DFS. This is a DFS, right? DFS can be done both recursively and iteratively, actually. You can use both recursion and iteration. But recursion is kind of cleaner. Just touch on the recursion. I feel people's brains are getting saturated at this point. Then God willing, next week we continue. I see something in the chat. What's DFS, please? Good question. Good question. Let's briefly just jump to DFS and then let's come back. So let's take something like let's go to our try friend. Okay, so DFS simply means depth, right? Like you go down. Depth. How do you spell depth? I almost get stuck with this. Depth. This looks cleaner. Depth. I think it's the first one, right? I honestly have no idea. I'm not an English major. Okay, so DFS means depth, right? We go down, right? Like we stand here, we go down, then we go down, then we go down. Like we go down till we hit rock bottom, right? Then we come back up and then continue another branch, right? That's what we call depth first search. We always try to go down. So let's say this guy here, let's say this tree. If I want to do DFS here, when I start here, I'll go down, then I'll go down, then I'll go down till I hit some rock bottom, right? Then I'll come back up here, then I'll go down again till I hit rock bottom. Then before I come back here, right? That's called DFS. If it's BFS, right? BFS is breadth, right? I think I can spell that one. Breadth first search. BFS does something different. BFS, when it takes this guy, so then explore them this way. It doesn't go down till it hits. No, it just explores the most. BFS is more like a family man, right? It likes to, family members first, to explore its closest neighbors first, right? So that one, if you start here, you consider this guy and consider this guy. Then when you're done, you take one of them. So let's say I take this guy, then I'll go and I'll take this channel, I'll consider this guy and this guy, right? Then I'll come here, then I'll consider this guy, right? So that's how, BFS works. DFS will come down, depth going down, but breadth, this guy wants to cover things like this, like a horizontal manner, right? That's how BFS works. Does it make sense? Does it make sense? Oh yeah, I see.
Yes, please.
Good. All right, let's go. Okay. So we're going to do this in a DFS fashion. I think it's kind of cleaner to visualize, honestly. BFS also works, right? Talented folks out there use BFS. Okay, so what we can do is that now look at the algorithm, right? We want to see if it's possible to complete other courses. Don't forget the question we're trying to solve here. Okay, so we can actually just start at any random node, right? So let's take node 2. We start at node 2. Then we'll be like, okay, is it possible to complete node 2, right? It's only possible to complete, course 2 if we can complete its prerequisites, right? That's basically the idea, right? It's possible to complete course 2 if you can complete its prerequisites, right? So let's say we have a function, right? Def completes prerequisites. Completes prereq, just called prerequisites, and it just takes a course and checks if you can complete its prerequisites, right? So I'd be like, okay, if the course has no prerequisites, right? So if graph, right? If graph of course is the empty list, right? We can simply return true. Does everyone agree with this? Does everyone agree with this?
Yeah, but I think this the last where we are showing our graph, drawing it inside, kind of using a hash map. I think 7 is to 7 containing 6. There's something wrong with it. It should be 6 containing 7, right?
Oh, really? Wait, let's take a quick look and see. Yeah, so 2 has a neighbor as 1, right? 1 has 4, 1 has 6, 5 has 2, 7 has 6, right? Like these are the prerequisites. Oh, I see. Wait. Yeah, these are the prerequisites, right? Like this is the course, and these are the prerequisites, right?
Yes. So if we saw like that, it means to take course 7, I have to take 6 before, which isn't the case. Get it?
That is. Oh, I think this guy is the tricky part here. Oh wait, did I change the diagram? Wait, to take course. Wait, give me a second. I think I see what you're trying to say. So to take course 2, we said you have to take course 1, right? Then to take course, I think it's possible. Wait, I think it's correct. Wait, what case did you mention? John, can you repeat the case you mentioned?
So what I'm saying is that to take course 2, you need to take course 5.
Yeah.
Not 1. Did you see it?
Oh, to take course 2, you need to take course 1. Yeah, and to take course 5, you need to take course 2. So to take cos 5, you need to take cos 2. To take cos 2, you need to take cos 1. To take cos 1, you need to take cos 6. Right? To take cos 70, you need to take
Oh,
cos.
okay.
Does it make sense?
Okay, all right. I was
Yeah.
thinking it in the opposite direction, rather.
Oh, okay. Yeah. So these ones, so it's more, I think maybe because this arrow is down, like it should be like 7, then also 6, right? So to take cos 5, you need to take cos 2. To take cos 2, you need to take cos 1. To take cos 1, you need to take cos 6. To take cos 7, 2, you need to take cos 6. Again, to take cos 1, you need to take cos 4, right? I hope that makes sense.
Yeah.
Okay, so now, so let's say you want to take cos 5. So let's choose anyone. Let's say you want to take cos 2, or I want to take cos 2. They're like, okay, to take cos 2, first of all, let's say to take any random cos. If you go and check your graph and that cos has no prerequisites, right? We can simply return true. So for instance, you can see 6. Let's put 6 actually should be in. 6 has no prerequisites, right? So if we call, if we check our graph and 6 is empty, we can simply return true, right? That means like, hey, we're done with this cos, we can take this cos, right? So now again, assume the function works. What is a function? Complete prerequisites. That's the regression trick we've been using all throughout. Assume this function works, right? Complete prerequisites. And it simply returns true if a cos can be completed, right? So we're assuming the function works. So let's continue. So we're like, okay, now to take a cos, right? We know that to take a cos, we have to check all these prerequisites, right? So for prereq in, how can we get the prerequisites? That's when our graph comes in. In graph cos, right? So for every prerequisite in our graph cos, right, we then check. We will throw in a few checks here, but let's just focus on this one. We can check if we can't complete a cos. So we can simply be like, if not complete, right? If we can't complete a cos, so you see, we're assuming our function works, right? Complete, let's call it complete cos. I think that's a better name. If we can't complete cos, so if not complete cos of this prerequisite, right, we can simply return false. Does this make sense? So what we simply do is that, so we take a cos, right? Let's say cos 2, come down. Let's say cos 2 here, right? Then we go through each prerequisite. So the first prerequisite is cos 1, right? Or like, if we can't complete the cos, why? We are assuming that this function works. The function we're implementing, we're assuming it works. We're assuming that it returns true if you can complete a cos, false otherwise, right? So if it returns false, this would be false, like this would be false. Let's use red. Returns false, this would be false, and not false is true, right? Then we return false. I'm sorry, we can't complete this, right? But if this for loop is able to end successfully, that means that all the prerequisites could be completed, right? Then we can return true here. We can return true here. This is like the bare bone like implementation, and it just works, right? But there's just a trick here to check cycles, right? Like this thing is actually going to work. Like if we do it on this simulation right now, you actually see it's going to work. But there's something we want to check, the cycle thing. And let's say we can simply check the cycle thing. So the cycle thing is, now, assume I'm trying to complete, and this is another trick for graph questions, right? We're just looking at the parts of a graph solution. So assuming we start at cos 2, right? Now we're going to track the path. So as you saw here, when we looked at this, where's the cycle thing we had? Where's Mr. Cycle? Okay, let's look at this graph. So assuming we started at cos 2, right? Then we went here, we see we're following a path. We went here, and assuming we came back to 2, oh, we've seen 2 before, and we just saw it again. That means that there's more than one way to get to 2, right? In the tree thing, that is what the thing we looked at, right? There should be only one way to get to that number. So if we see it again, that means there's a cycle. So let's kind of trace our path. So what we do, we pass another extra argument to our function. Let's just call it visited, right? You can actually do it without passing the arguments, honestly. You can just use the visited outside, but let's just do it this way for clarity's sake. So visited. So before we start another recursive call, we're going to put the current course to our path, right? We're going to like track it. Let's just put course here. We just put course here, right? So to make it clearer, please come down. Okay. So 2, right? We put 2 in. So now visited contains 2. Then we call, we consider 2's prerequisites, right? Then we call it on, let's say 1. 1 is the first prerequisite, right? Then if we called 1, right? And then we come and we have seen 1 again, we return false, but we've not written that code yet. But let's assume we go through 1's prerequisite, 4 and 6. And then we see 2 again, 1's prerequisites, right? Then we trigger it on 2, right? We realize that then that means there's a cycle, right? So we should simply return false, right? So what we can simply do here is that if cos in visited, so this is simply how you check a cycle. If cos is in visited, return false, right? That means that, hey, if I'm currently processing you, so think of Visted as something you're currently processing, right? So if it's a course you're currently processing, you put it inside Visted, right? So if I'm processing you, right, and then I come and see you again, that means there's a cycle, right? That means that, I'm trying to satisfy you, but then somebody also needs you, so you can return false, right? But if I am done processing you, I can simply remove you, right? So if I'm done processing you, and that is where you write it here, Visted.remove course. And that is all. Let's change this guy to blue. I just want to see the parts of a graph DFS. This is like the fundamental thing. Return true. And that's basically the question. This one last optimization we can do, but this should actually solve the question, right? So again, if the course has no prerequisites, return true. Then we're now come to start processing you, right? So let's add you to our path, Visted, right? Then we will, like, for prerequisites in graph, we consider your prerequisites. Then we call, we try to complete your prerequisites. That's what we're trying to do here. If then we come here, if the course is a prerequisite of its prerequisites, that means it's not possible, right? It's a cycle. We then return false, right? But then if you're able to complete all your prerequisites, that means this for loop has ended. Then we can remove that course from the path. Then we can return true, right? So if we can, this is a form of like kind of backtracking thing, then we can return true. And that is simply the solution to that question. There's an optimization you can make if you look carefully. So for instance, if you look at this carefully, right? Look at this carefully. If you take course, let's say course 2, right? Course 2. Let's take course 2 here. Actually, let's take course 6. Course 6. I want a different one. I want a course that has multiple ones. So let's assume, right? Let's assume that course 7 also depends on course 2 here, right? Right. The moment I know I can complete course 2 here, right? So let's assume I tried to complete course 2 and I was processing course 5 here. Then I was able to feel like, okay, I can complete, course 2 here, right? So course 2, course 2 also depends on course 1. So the moment I know I can complete a course, I'll just set its prerequisite set to the empty sets, right? Why? Because I don't want to trigger recursive call on 1 again, right? So as you can see here, we return true. Now, why can I do this? So all I'm trying to tell you is that if you can complete a course, the moment you realize you can complete a course, you come to this part, right, where you have to return true. Just set graph of that course, right, to the empty list. You can even use something. It can be like completed. Can you have a different dictionary completed? But if it's completed, just sets the course to be true, right? So you don't make unnecessary recursive calls, right? So if I do this, so let's say when I was trying to complete course 5, that is when I completed course 2. If I come to course 7, I want to complete course 2 again, right? The moment I get to this guy, this course 2, because of this case, because I've set it to the empty list now, this part will catch it for me, and I don't have to process course 2 again. So just an optimization thing. Does that make sense? But there's a way to optimize it where you don't have to, make recursive calls for things you've already made recursive calls on. Something like dynamic programming as we did last week, right? It's not really dynamic programming, but just like an optimization thing, right? If you don't want to manipulate your graph, you can simply use another dictionary, completed, where each time you complete a course, right? Each time you just set it to be true. So here you can just add another base case. If completed, right? If completed, of course, right? If completed, of course, that is if it is true, return true, right? Return true. And that is another optimization you can do. So this is basically the parts of a typical graph problem using DFS. First, just sketch out the bare bone structure. This is the base case. This is simply the recursive case. And this is actually very similar to trees, right? For trees, we just needed to make 2 function calls here, right? But for a graph, the neighbors, right, can be more than 1. That's why we're using a for loop here, right? So the neighbors can be more than 1. For a tree, we just needed to, make 2 calls, right? Node.left, call the function, or node.left, call the function, node.right. But here we have to call the function on as many prerequisites as possible, right? And they can be more than 2. So that's why we're using a for loop here. Then you just, write your check here, then you are done. Understanding this thing is really going to save you a lot of time and a lot of effort, trust me. Yeah, we're actually a bit over time because we have to do a different data structure and stuff, but it's basically, kind of like the gist of graphs. We continue, God willing, next week, but I'll send a couple of questions that people can go through. Yep, Iris, your question. Any questions? Yeah, Iris can go ahead.
Please, with the matrix, the representation of the graph. What if the graph is undirected graph? Oh,
good. Yeah, so this is undirected. That's a good question. Yeah, we can do the same thing here, right? So let's assume it looks something like, let's make this one undirected. It's the same thing here. So that one, what you do, actually, we should have actually done. So here, so right, there's an edge from 1 to 2, right? So both 1 and 2, right? both 1 and 2 have an edge, right? So 1 to 2, you write your edge here, then 2 to 1, 2, you write the edge here, right? So it's just something like this. So you always just duplicate it, right? So 3 and 4, right? 3 and 4 also have a similar thing. So 3 and 4, 1 here, then 4 and 3, you have 1 here, right? Which means that 3 is a neighbor to 4 and 4 is a neighbor to 1, right? The relationship is in both directions. Does that make sense? We can even do the same thing for the adjacency matrix, right? So assume that, you know, you want to do this. So the same thing, you do the same thing here, right? Like if you put, so let's say it's like this 1 and 2, right? There are quite some questions that will involve you to actually do this, honestly. So 1 and 2. So if you put 2 here, right? For 2 also, you put 1 here, right? Everybody gets to do it, right? That's actually how it works. Does that make sense?
Yes, please.
Okay, good. Any questions? Any questions? Any questions? Yeah, I know it's a bit, what do you call it? It's a bit a lot, right? But I see graph actually makes sense, right? It actually makes sense. The of algorithms we'll be considering in the next few weeks, we consider some popular algorithms, like, you know, people know Dijkstra's algorithm already, but, you know, we implement it in a cleaner way. I know that this one is a bit verbose. We also consider one of my beautiful algorithms called Union Find. It's so cool. Like when I got to know this algorithm, it was so nice. Then we also consider what you call the path compression algorithm. So let me just give you a gist of, you know, find what we do this next time. So simply, one application of it is number of connected components. So assuming we have a graph like this, right? So we said a graph can be disconnected, right? So let's assume this is a graph system, right? We're like, how many connected components are there? And here there's 2, right? There's this 2, there's this 1, there's this 1, right? Like these ones form one graph, this another. We want to see how many connected components are there. Assuming we had another node here, this would be 3, right? Assuming we had like another graph here, this would be 4, right? The algorithm is so pretty, right? Union Find. It's actually just simple. It's simply a matter of, you know, just joining all this together to form one, and so on and so forth. Yeah, it's very cool stuff. Then we also think like minimum spanning tree. We consider things like and so on and so forth. Yeah. Any questions? I hope I recorded this session, and I think it'd be good to rewatch it. And we'll also I'll send a few questions on tries, then a few questions on graphs, including cost schedule. There's actually another cost schedule. That's on cost schedule. There's actually another thing on cost schedule. To realize that the order in which the courses are going to be completed is going to be the courses with no prerequisites are going to be completed first, right? Because you see, if you start the recursion on, let's say, course 2, right? Course 2 cannot be completed, right? You have to go down to hit maybe course 6 and be like, course 6 is done, right? So the order is going to be like 6, comma, right? Then when you're done with 6, then maybe you can be like maybe 4, right? Or maybe 1. We can't even complete 1, right? Because if you're done with 6, 1, 2 still depends on 4. So then maybe 4, right? Then maybe with 4, maybe then you can complete 1, right? You're like 1. Right. So there's another question that asks you the order in which the courses will be completed. And looking at it, the courses with no prerequisites, right? The courses with no degree, with no out degree, sorry, the courses with no out degree are going to be completed first, right? And the very common thing, right? That no out degree nodes are usually, you know, processed first because they have no dependency. And the last thing I'm saying is that this is also a form of what we call topographical sorting, topographical sort. We can actually discuss more, God willing, next week. All right. Any questions? Anything confusing? I know. Probably not so confusing, but that's it. Anyone has any questions? God willing, next 2 weeks you'll probably do more problems on graphs, but I just wanted to get the main intuition. Yeah. All right. Anything? Anyone? Was fast. Yeah. If anything, just send the questions to the GSA channel, and we should definitely get back to you. We have to hop off now, so later then. Right, everyone. Bye.
Bye. Bye.